Hello, this is Chapter 1, Part 4, Section 1.9. In this section we're going to look at some applications of the work we've been doing on lattices, namely the effect of temperature and pressure on the lattice parameters. First of all, let's define two terms. You probably know them already. One is isotropic properties of a material, and those are the materials that are independent of direction. So no matter which direction you heat it or squeeze it, it really doesn't matter. On the other hand, many materials have anisotropic properties, and those are the properties that depend on direction. So sometimes, if you look at Young's modulus along one of the directions, it'll be different from another direction in the crystal. So the first topic we're going to look at is the effect of temperature on lattice parameters. And from thermodynamics, you probably remember the linear coefficient of thermal expansion. And in that, we have a constant pressure. So we're looking at the change of length, and this is going to be a lattice constant or something related to it. With respect to temperature, at constant pressure, we have a intensive property for temperature and an extensive property for length. So the coefficient, if it was left like this, would be a extensive or depend on the amount of stuff you had. That's not really a good idea for a coefficient of thermal expansion. So in order to do that, make it intensive, we divide through by the length. We can bring that length inside the derivative sign, and we get the derivative of ln of L with respect to T at constant temperature. So that will give us the linear coefficient of expansion. So now let's apply it to crystallography. We can measure our lattice constants at various temperatures. Here's the temperatures down on the side, and here's the lattice constant. Here's the A and the C constant. This is for urea data. And we can plot the temperature along the x-axis and the log of the lattice constant along the y-axis, and the slope will be the linear coefficient of thermal expansion. Let's look at the actual data. We can run a least squares equation to fit the data, and from that we see that the slope is 5.23 times 10 to the minus fifth per degree Kelvin. Well, this is a very accurate way to measure the effect of temperature on lattice parameters. We can also do a similar type of study for the effect of pressure on lattice parameters. As we go deeper and deeper into the earth, the crystals are subject to greater and greater pressures. We can duplicate that in the laboratory with the diamond anvil. Here's our poor little crystal sitting here being stressed by two beautiful diamonds, and this is called a diamond anvil. And the diamond is simply is very strong, so it squishes the crystal. In fact, when you actually do the experiment, it's a little more complicated than that. Here's our green anthracene sample sitting in here, and our diamond anvil's up there. We put a gasket around here, and we put some fluid inside the gasket. If you just sort of squeeze on it without that, you'll most likely crack the sample. Here's an example of some of the apparatus at Virginia Tech. This is a diffractometer, which measures high pressures for the geology department. Again, the formula for the linear coefficient of compressibility is really quite similar to the linear coefficient for temperature change. Only here, where of course we have the change of length with respect to pressure at constant temperature, again we have the same problem of extensive and intensive properties, so we divide through by the length. We have a negative sign here because as you squeeze the material, the lattice constants get smaller. The greater the pressure, the smaller they are, so to keep the coefficient positive, we put a minus sign there. And now we can go ahead and do a similar plot. Here's some material from anthracene and under various pressures, and here is the plot. Now if you notice this plot, we would kind of hope it would be a straight line, but it's not. There's definitely a curvature to it, so we can't do it as simply as we did the temperature place, but we now instead measure the mean linear compressibility between two pressure points. So we simply select two relatively close points, and we take a mean compressibility averaging between the 2 points. So here you have the change in the lattice constant over the change in pressure, and this 2 gives you you're taking the mean. So that will give you an approximation. It will give you some form of a lattice compressibility, coefficient of compressibility. And finally, let's take an example with anthracene, and here are some of the values of anthracene. And if we take these two values, 6.07 gigapascal up to 6.70, we see that the angstroms at 607 are 7.5646, and when we increase it, when we increase the pressure to 6.7, then the length of the side goes down to 7.5408, and we take that average, and lo and behold, we get a value of 0.005 gigapascals inverse. Okay, that's the very end of chapter 1. I hope you've enjoyed it. That's all for now. So long, folks. Bye.